So we could estimate this data with some hypothesis function. The goal of this is to get some type of model that will accurately predict a housing price given the area of a house. So this is one example of such a hypothesis. And now onto how should we represent the hypothesis. So we all know from basic algebra that the basic equation for a line is y equals mx plus b. So for this problem, we'll just use h as the name of the function and theta 1 and theta 0 as replacements for m and b. So these are just parameters that we have to tune through linear regression so that we can get the best possible h for our data. And theta 0 has a special name called the bias term. So the reason why I had to name it as like theta 0 and theta 1 is that it makes it easier to generalize our hypothesis when we're talking about a different type of data. So in this case, there's only one feature of the house, that's area. In another case, we might have more data. We might have another feature, such as maybe like the rating of the school district or closest distance to public transportation. So that would increase the number of features. So in the case of multiple features, like the ones I just mentioned, we would have another theta value in front of that feature. And that would make our hypothesis function a little different. So just to generalize, for n features, the theta would be a vector of theta 0, theta 1, all the way until theta n. And I just put transpose, which means instead of a row, it's a column. And x would be a vector with 1, x1, x2, all the way till xn, and also as a column. So that simplifies things, and it kind of makes sense now why I replaced it with theta. Because we can now represent this original function as h is equal to theta transpose times x. And if you look down here, if you want some linear algebra review, it's this operation right here, where this row is multiplied by this column to create something like this. So since we are trying to find a good hypothesis through linear regression, it's important that we should be able to distinguish between what's a good hypothesis and what's a bad one. So these are 3 lines that I've drawn on the data, 3 hypotheses, and we can see that probably one of them is worse than the other 2. For me, I see that the green one, it doesn't really fit the data as well as the other 2. So numerically, we want to represent this in some way. And the way we do that is by using a cost function. So in this case, I used the cost function called mean squared error. And what it's essentially doing is getting the difference between the predicted price and the actual price. Predicted price and the actual price, and then squaring that difference and doing that for each of the data points in our data set. So that's what this part here is doing. And summing it up, and then dividing by the number of training examples. And I should mention that m is the number of training examples. So in this case, there would be 8 training examples. So j of theta, our cost function, should give us a good idea of how our hypothesis is performing and show us whether one hypothesis is better than the other. Just by noticing that j of theta should be smaller when our hypothesis fits our data better, since the difference between predicted and actual price should go to zero. So now that we have an idea of the cost function, we know that probably the best approach is to try and just optimize this cost function to go to zero. And the way we do that is by using what's called the gradient. Gradient is kind of like the derivative of a function, except it has a direction. So let me actually go here. So the gradient of a function is points in the direction of steepest increase. So when we go in the direction opposite to the gradient, we'll start heading towards a local minimum for the function. So this graph here plots j of theta, and w can also be used for theta. It means the same thing. I think it stands for weights, but w and theta are both like parameters. And over here, there's on the y-axis we have the cost, and on the x-axis we have like different values of theta or w. So this is like the optimal place to be. So if you chose a theta value here, it would get you a very low cost. But you'll probably start somewhere up here farther away from the minimum. So the idea is we have some function to continuously change our theta value. So we go in the direction opposite of the gradient and go slowly towards our local minimum, or our global minimum, yeah. Yeah, so that whole process that I just described is the idea behind gradient descent. The idea is this: you start with some theta value, and you take that theta value and you subtract the gradient of the cost function. And a here is the learning rate. It's just some small number. And if you take the derivative of the cost function, it ends up being a partial derivative. It ends up being this thing right here, which you can see it's somewhat similar to the cost function, except it's multiplied by the value of the specific feature of correlating to whatever theta you're looking at. So essentially what gradient descent is doing is you go through all your theta values. In our case, for the linear regression I talked about earlier, the housing data set, there was only two theta values. So you'd iterate with gradient descent, and you'd update those two theta values to get closer and closer to a point where your cost function is closer to zero. Yeah, and this is a 3D representation of what gradient descent looks like. You're going to start from some higher point, and you're trying to go slowly towards a global minimum. All right, so now that I've briefly gone over linear regression, I'd like to go over logistic regression. And it's a little different from, well, it's actually a lot different since it's doing a classification task instead of a regression task, even though it's called regression. So just to get right into it, let's look at an example. This is an example of tumor classification. Say you have like some data and you have sizes of specific cells, and you're trying to see whether the size or of specific tumors, and you're trying to see whether how to determine whether a tumor is malignant or benign based off of the size of the tumor. So if this is an example of the data you got, you can see that it's kind of hard to fit linear regression to this model. And since you say, okay, so y equals 1 means our data, the tumor was malignant or positive, y equals 0 is the tumor is negative or benign. Sorry, y equals 1 is positive. You can see that there's no reason for any data points to be above 1. So it doesn't really make sense to have a function that goes past 1. So that's why in logistic regression we use a slightly different function. So the function we would use in logistic regression is called the sigmoid function. And essentially what it would do is it would squish all of our data, all of our predictions in between 0 and 1. So now it makes a whole lot more sense when we output a value 0.9, 0.8, and we never output values more than 1 or less than 0. So, and this is in the case of a binary classification. So true or false, and only 2 classes. Also, with logistic regression, we want to pick some type of threshold and just say if it's below that threshold, it goes in one class, and if it's above that threshold, it goes in another. Since, as I said, this is a classification task, you don't want any continuous output. So we can interpret something like h is equal to 0.7. Let's say we input some data of a tumor that's this value big, and it gives us an output 0.7. We can interpret it as the tumor has a 70% chance that it's malignant. And we can always adjust whether the function should output malignant or benign. Yeah, and this is just the sigmoid function again. All right. And then the cost function for the for logistic regression is a bit different. It's going to use a negative log of the hypothesis if y is equal to 1, or the negative log of 1 minus the hypothesis if y is equal to 0. Remember that the hypothesis is our prediction. H of x is going to be our prediction. So if we think about it, it makes sense intuitively. I plotted the graphs over here. So if y is equal to 1, negative log h of x would be this function right here, negative log x, which is this blue line. So if y is equal to 1, if y is equal to 1, it's the blue line. And if we predict 1, we want to get like a really small error. So that's why it gets to 0 over here. But if if our hypothesis outputs some value that's closer to 0, it should give a really high cost. So it makes sense why this first part works. And the second part is similar. It's this red function right here. So you can think of this as the hypothesis and the y-axis as the cost. So, and this red line only applies when y is equal to 0. So if y is equal to 0 and the hypothesis predicts something close to 0, it should give a low cost. And if it gives an output closer to 1, it'll give a high cost. And this function right here is just the top function rewritten. It's, if you plug in the numbers, you'll see that when y is equal to 1, this part will cancel out. So you're left with the original term, the first term. And if y is equal to 0, this term will cancel, so you're left with this original term. And the great part with logistic regression is that the gradient descent algorithm, the gradient descent calculation is the same as linear regression. So you take the derivative of the cost function and you end up with the same cost function here. Yeah, so I just talked about binary classification, but the idea can be easily expanded to multiple classes. So the steps to do that is to first create a hypothesis for each class, and then input test data into each class's hypothesis. And then all you have to do is select the class that gives the highest probability value. So an example of that is like in digit classification, like MNIST, if you've heard of it. If you use their data and you're trying to classify a bunch of handwritten digits into 10 different categories, you can train 10 different classification hypotheses to recognize the digit and input your test data into each of the hypotheses, and then take a class with the highest probability that as the chosen class. Yeah, so I wanted to go over some problems you might encounter when training a model. So the first thing is overfitting. These are just a bunch of data points, and let's say you trained a linear regression algorithm on this data. First with just theta 0 and theta 1. So it would be a linear function. You got this and you realized, oh, the cost is kind of high, and also it looks like it's not supposed to be a linear function. It kind of has this curve to it, right? So this is what's called underfitting. And what you might decide to do is you decide to add higher number polynomials. The way you do that is you kind of create a dummy feature by squaring your original feature, and that would create some higher number polynomial here. So if you square your original feature and input it as a new feature, you'll have a theta 2, a theta 2, a theta 1, and a theta 0, and you'll be able to have some function like this outputted from your linear regression. And you realize, okay, the cost got lower, so you're thinking, okay, I'll add another like power feature. So if you do something like x cubed and you add it in, you might get something that has a very low cost, um, but that's not always a good thing, since in this case it seems like it's overfitting the data, which means that if you got newer data or data from the real world and you put it into your algorithm, it would have a high test error. It would have a high error. So one way to prevent this overfitting is to use what's called regularization, which will um, which will penalize using a lot of thetas. Sorry. Right. So this was that cost function I showed earlier for linear regression, and here is the added part for a regularized cost function. Lambda is some number, and theta squared. You can see we're just summing up. We're going through all the theta values and squaring the values. So this will penalize using unnecessary thetas. But now that process of like regularizing your cost function will introduce a new hyperparameter called lambda, and that means we'd have to use what's called a validation set to find this new parameter. So we can use this. We can do a split across with our training data set and split it into three parts. One would be called our training set, one would be called the validation set, and one is called the test set. And the goal of this is that you would use like 80% of your data to train um, your model, and then use 10% to choose the regularization term. So you train your model, and then you'd get a bunch of these different um, uh, functions. And with your validation set, you'd realize that the validation set, once you put in a bunch of extra points on here, you'll realize that this model probably generalizes better to the validation set. So that would help you choose a theta value here instead of something that was too high. Yeah, instead of something that was too high. Yeah, and then there's also the test set, which would be like how you can interpret it as how your model would perform on real world data. Um, and you can't really use the validation set for that anymore since you already kind of um, not explicitly but kind of trained it with your validation set since it was responsible for picking your regularization term. Yeah, so now that I went over that, I want to go to this. Okay, so this is just a demonstration of single variable linear regression using sklearn. All right. Yeah. Wait, hold on.
Albert, you can tell them to follow along on their own collab if they can.
Oh, okay, okay. Yeah.
So everyone, yeah, you can provide instructions for that, Albert.
Okay. Um, so if you guys can you guys open a Google Colab? And I mean, I could even share this, but I guess you could follow along for now since there's not that much code. Um, so go to Google Colab and see. Start a new notebook. All right. And here you can just add code using this button right here and just follow along over here. So I first import a bunch of packages that will help us with dealing with the data. So NumPy is an array processing package. Matplotlib will help us view some of our data. Pandas will help with some data manipulation. And I think this is necessary for us to view the Matplotlib um, displays in our notebook here. So over here, you want to import the linear regression model from sklearn. So scikit-learn is this library that's pretty nice that comes with some standard machine learning models. And then I'll also import train test split and this, which is a data set, load Boston. So the Boston data set is this older data set with these things. It's a bunch of neighborhoods, 506 neighborhoods with um, different features over here, like per capita crime, lower percentage, lower status. But what I'm interested in right now is the average number of rooms per dwelling and the median value of owner-occupied homes. Okay, so first you want to load in that data using load underscore Boston, and then put the Boston dataset dot data into a pandas data frame, and also give it the column labels, which are also easily provided by the sklearn dataset. And you can also see the first few uh, data examples. And this is the only part we're interested in, the Boston average rooms per dwelling. And here I'm just taking out the average rooms per dwelling and labeling it with the columns, putting it in a pandas data frame and looking at it, and then also taking out the target, which is our array of housing prices. Now, I did this earlier, but I guess I accidentally repeated it. This function will help us split the train and test set. So it'll help take our data and then split it into a train and test set randomly. Um, and here I selected that I'll put 20% into our test set. All right, and here we are training the model. So, yeah, so creating a linear regression model object, and then using model.fit with the train data, so x train, and giving it the y train values. And here I'm just evaluating the model. We should start from the top, actually. Yeah, okay. So here we got our training cost and our test cost, and I plotted the linear regression model on our training data and also the test data, just to see how it fared. Yeah. All right, so that was single variable linear regression, and now I'll go over logistic regression.
Hey, Albert, do you mind if I just interrupt you
So,
really quickly? I just want to share something
yes.
because I might have to head out in a bit. Uh, yeah, you can get back to it in just a bit. So I'm actually going to, for those of you who are still on the call right now, I just want to share a link to a forum. This is basically for an industry project. I wanted to share it right now. I didn't want to interrupt Albert with this lesson, but it's for an industry project. Basically, if you're interested in working on machine learning stuff in a industry setting, so we have a partnership with the company, and you could work on industry, basically ML stuff directly on an industry project. Um, Please do take a look at that forum and send your information. And then we're going to actually start like looking at people the end of this week. So this is just something else that we're doing part of this club on top of the teaching. So if you have any questions, you can just email us or ask on the Facebook page. Okay, that's it.
All right. All right. Yeah. So this is the second example of logistic regression. The imports are similar, but this time I'm loading a different data set. This one's a digit classification data set. So the goal here is we have a bunch of these images, pixelated images, 8 by 8 pixels, and we want to determine what number it is. Yeah, so this is just an example of one of the numbers. And here I load in the data and the target in the same way as last time, split the data the same way, and just loading the logistic regression model and fitting it on the training and X train and Y train data. And I just made some predictions. So log model dot predict X test will give us what our model predicts the value to be of all these images that were in the test set. And this confusion matrix function provided by sklearn will give us show us how good our model is doing. So everything on this diagonal here is are times where the model correctly guessed the test set image. So if it was a 3, it guessed it properly. And then all these ones outside of the diagonal were mismatches. And I just used the model.score to show the percentage that the model guess did correctly on the test set. And I can also share this along with the slides later. Yeah. Right. Oh yeah, so these are the resources I used for the slides and this these two examples. So if you want to look at that, and also I know that some of you wanted like a mini assignment. So what you guys could do is add another feature to the single variable linear regression and see how that affects the performance of the regression. Um, Maybe try LSTAT, which is a lower percentage of population, and also try to make a polynomial regression by adding
Obviously, I
maybe
haven't
the
opened it.
room dwelling
What
squared
made
as
you
a
like
feature and
that?
see how either of these additions affect the tester.
Are you triggered?
All right.
Not really, actually.
And that's pretty much it. So if anyone has any questions, now's the time.
Ugly.
Last Chewbacca, more brown carrot top, but yee.
Um,
Ugly.
Okay, I need to catfish him back. What should I even say
right.
to that?
I
What
think,
do I even say to that? Yeah, I feel that.
yeah, I think no one has any questions. If you do, feel free to reach out.
Yes, brown color, girl pose, dude, hit on your
Okay, yeah. Thank you. Next week we're going to be going over k-means,
Yeah.
so please
I
come by
see
for
that.
that.
Yeah.
What you up to? Oh man, I can't wait. It's gonna be the. I wish we could see the look on his face.
All right. If that's it, I think I'm going to end, unless anyone has any final questions.
Let him.
Huh?
If not, let's see how long this goes. Because, like, I want you to just be like,
Dude, how can he not know? Like, he must have been a really bad boyfriend. You guys were together for 6 months. He doesn't know you're 4 friends?
right? But I was like, oh yeah, like, just like you gotta make him feel bad at the end of the day. You gotta be like, look, I wasn't interested in you. This was for the meme.
Oh my god, yeah, for sure, anything, bro.
Oh my god.
I'd be like, I wouldn't do Nisha like that. Like, fuck off.
I mean, if you want, I just don't recommend it. Like, it was bad.
Did you see the picture he just sent me, Nisha? What was I gonna say? Is everyone leaving? Yeah. Yeah, we need to do that. That's so funny. Also, did you make me a post?
No, not yet. Okay, I'll do that on our call. We'll talk about it.
Okay. Okay, I will talk to you later.
Yes, I'll call you later tonight.
Okay, bye.
Bye.
Is there anything for us to discuss?
Yeah, if not, I can end the call.
Great session, Albert. I really like the content.
Oh yeah, no problem. Yeah, I think that's it. Yeah, I don't think there's anything else.
Okay, sounds good. I'll see you guys
All right.
next week.
All right, thank you.
Bye.
See you. Bye.